kind of push you guys a little farther in here and just go ahead and like work on identifying the difference between a strong acid and a weak acid. But I don't push you too far because there are ways to actually literally put numbers on it and literally figure out how much acid would be in water based on whether it's strong or weak, and there's a whole lot to it. But I can give you some kind of rules of thumb that are helpful. But does everybody have this general idea? I just want to make sure you don't miss something. And it has to do with our language and how you hear about it. And you go, okay, this is an acid. Everybody okay with hydrochloric acid? That's an acid. But the truth is that's not an acid until it falls apart. And this little thing gets cut loose from, it's like the Tasmanian devil. It's a full proton, it's positively charged, has no electrons whatsoever, so it literally starts ripping metals apart. Does that kind of resonate? Does that make a little better sense? That's the business end. So really, if I was being accurate, I would say that's an acid. But what we know is this stuff, when it gets in water, makes the water acidic, right? So that's kind of where those wording gets changed. But I could, now see how I'm doing with my arrows? I'm doing that on purpose. I'm saying this completely falls apart. Okay? There are things that don't fall apart. I'm going to put this up because it's probably the most familiar to you, because you eat this all the time. This is acetic acid. So anytime you have hot wings, you use vinegar on anything. Vinegar and oil dressing, right? It's got a little bite. That's that little baby amount of acid that gets in there and goes, oh, that's got a nice little snap to it, right? Or I could draw other ones like this that make like red pepper or whatever that has a little bit of bite. Certainly, it does not fall apart very good. True? So we call it weak. So if I was drawing it with arrows, I'd be like, and just a little bit of this. And this is the acetate anion. This is like you learn in your polyatomic ions, the acetate. If you look on your polyatomic sheet, it gets drawn different ways, but it's the acetate. This is good because you guys know enough organic chemistry. I can give you the full story, right? This is ethanoic acid. That's that. Remember carboxylic acid? Right? That's the acid part that falls off and you're left with. This is literally what an acetate anion really is. It's F. Right? If you were taught, you use in formal organic chemistry wording, you'd say ethanoate, which is, but you got it. You got the F, 2 carbons, right? And then it's a derivative of carboxylic acid. But what do you need to know out of this? And it's just this weak versus strong. Strong just fully falls apart. When it drops in water, this is there. I mean, you don't meddle around it, will rip it up. You don't want it on your skin, it'll burn holes in you. You don't want to drop it on the floor, it starts burning holes, right? This is bad stuff. This stuff, Why? Because it doesn't come apart until something asks for it, basically. That make sense? So if I start pouring this on a base, it would start reacting. Until the base is gone, then it'd stop reacting and you'd still have a lot of this left over. Is that okay? And I say that because it, like you can imagine my body is full of these weak acids. They're used as needed. If I need to adjust, like I need to neutralize, I take in something that's very basic and that might hurt me, it will just adjust and start to neutralize it. And vice versa. Is that okay? So that's the point. I just want you guys to understand when we say weak acid or strong acid, we mean strong acid fully disassociates, gets lots of H plus in the water. Weak acid just get a little bit of H plus in the water. Because most of that acid stays together. And so I just wanted to show you some structures that when you look at them, you go, oh, these are weak or strong acids. Now, the nice thing for this level of chemistry is acids are usually written with the H leading, right? And that's why when I write this, we don't put the H's after, we put them before because we're trying to clue you in it's an acid. All right? So even though these look very similar, if I drop this in water, it stays like this with very few H pluses coming apart. I drop this in water, one of the H pluses falls off immediately. And you have, if I put a mole of this in water, it would fall apart and there'd be a mole of H pluses almost immediately. If I put a mole of this in water, I'd get maybe 0.001 moles of H plus. The rest would just stay together. That's weak versus strong. Is that okay? Does that make sense? Okay. So now with that in mind, then I'm going to actually show you ways to know weak from strong. So there's just kind of two kinds of acids that you need to be aware of. The first one's just attached to whatever the anion is on the table. So that's to the right of the stair step. So I could pick something off the right of the stair step. Chloride, sulfide, and this will be in its anionic form, right? The charge they like to take. And then I could just attach H's to them, and that makes the acid. So I'll just throw a couple up. So okay, so that would be HCl. There's the acid. How many H's would attach to this? They're H pluses, by the way. 2. How many would attach to this? Perfect. That's it. That's one form of acid. Pull your polyatomic ion sheet out, or at least something that has them. This is also kind of substituting works because it has the polyatomic ion, which is kind of handy. Give me a couple polyatomic anions. Anything off there?
Chlorate.
What?
Chlorate.
Chlorate. ClO4, is that right?
3.
3. Thanks for picking one that I didn't know. So that's good. Like, oops. Okay, now if I put an H on it, right, how many would it attach? 1. So that's, see, that could also make an acid, right? See how this is working? Give me another one.
Would that mean it's a weak acid?
Hold the fort on that. You're getting ahead because I want to make sure we all get there together. No, strong. But go ahead. I'll show you here in a minute. Give me another couple more. Chromate? Chromate, thank you. Gosh, thanks for picking all the hard ones. What is chromate's charge? I don't even know it. -1 or -2? Oh, it's like, I've been doing this for years, and you guys pick the ones that I'm like, I haven't memorized that polyatomic ion. Anybody, something I know, carbonate, sulfate, something. Give me something. Give me a couple more. I don't care. Phosphate, yay! I know that one. What's the charge? 3-, correct? So how many H's would attach?
H3.
Cool. Good. One more. Just got it. No, this is plenty. We got 3. That's good. You ready? Now watch. I just want you to know that, so that this is where I'm asking you to go a little farther. This is a little bit of but it might be helpful for you. Because if you think about things that you work around and you look at it and you go, it's a strong acid, you should be like red flags going off and like, be freaking careful with this. Like me today, if I come in, if I know I'm going to pick up a strong acid, I'm going to have gloves. Right? If I get any of that on my skin, I'm leaving class and going, right? It's going to be a mess. Weak acid, you guys mess with weak, you pour vinegar on you probably all the time. You don't even think twice about it. Boric acid, I don't care. You with me now? See the difference? So I would like for you to be kind of educated. The other part about it is also some of these odd things that you may not think of are acidic, because that's pertinent to like your mouth, right? Because we don't like acidic environments in our mouth, because that leads to cavities. Okay, so there's that. Now that I've got that out of the way, let's just, by structure, we're going to go weak or strong. Okay? This family is just a little memorization task. Did you pick that up yesterday? I just said, hey, just look here. This is all you have to do. See that little row of 3? H's attached to those are strong, chlorine, bromine, iodine. H's attached to those are strong. Anything else is weak. So with that in mind, we can go through this and go strong, weak, weak. Yay. And I over-exaggerated because I said, well, this won't even hurt you and all that. But that hurts you for other reasons. Not because it's a strong acid, because it's not. It hurts you because fluoride ions are kind of dangerous when they're in an acidic environment. That's actually kind of important to you guys. They do weird things. All right. Good? And I think this is where we are about to go. How do you do these? It's really interesting that the more oxygen, here's the way to think about it. The more oxygens you have, the weaker the bond becomes. So therefore, it makes it strong. The more oxygens weakens this bond, so that pops off easier, therefore making it strong. So if I translate, I say more oxygens makes the acid stronger. So this one's an interesting family, because you have ions that work all the way from here to here to here to here. They're all possible ions, right? Unfortunately, I don't know, are they, can you look on your polyatomic, are they all -1 charged? Yeah? Oh, yay. Okay, good. So it's going from weaker to stronger. But where do we go weak? Where do we cut off? Where's the cutoff? Where's the weak and where does strong begin? Okay? It's called the H+1 loop. That's where we're going. You take the H, you add 1 to it. That's 2. I'm not saying there's 2 H's. I'm just saying however many H's, just add 1 to it. Okay. And then compare it to the number of O's. If the O's are greater, strong. If it's equal to or less, weak. That's it. And I just keep it simple. I just say, hey, if the O's are greater, it's strong. Anything else is weak. Well, what's anything else? Equal or less. Right? Think about that for a minute. All right, so here we go. We can start classifying. O's are greater, strong acid. See here, we can do the trend here. Ready? O's are H+1 is 2. O's are greater, strong. +1, 2 equals, 2 is less than 3. Oh, now they're equal. Weak. The rest are weak. What about this one? 3 to 4? Strong. Phosphoric acid. By the way, Breaking Bad, this is the stuff you use to digest flesh. Right? This is the magic stuff. Right? I told you I used to get rid of bodies, right, for a living. Did I not tell you that? Yeah, so I literally know how to make bodies turn liquid and go away in the sink. Well, anyway, we'll keep going. You probably don't care to know about any of that. Weak or strong? Weak. By the way, I'm not joking, I did that. Not that you care. I love to get that to students. It's true, though. All right, so I used to work in radiochemistry, and we used to digest, I know, rabbits. See, I used to say that, and students would get all up, like they'd be laughing when they thought it was humans, and then I say, no, actually it was rabbits. Then they get upset, and then I'm like, what is wrong with you people? But anyway, so we would digest rabbits that were on rocky flats, like where there's been nuclear activity, to see if the rabbits had radioactivity in them. So along the way, I had to learn that process by which you dispose of bodies. And that's what, the mob does also. Good people in the mob. I mean, I don't want you guys to be bad killers if you become a killer. If I train you up, I want you to be good at it. But anyway, so that, yeah, I used to do that. So the two magic stuff is phosphoric acid, which is weirdly weak. But what it does is it interacts with bones because of the phosphate. That's a whole nother story. It has nothing to do with acid-base chemistry.
Where are the rabbits radioactive? I grew up over there.
No, not out on the site. But in the, as you know, like in that area, yes, there was a release inside the facility, so plutonium. So,
Yeah, I
but
grew up right over there.
yeah, so I know.
I know.
You know all about that stuff, huh?
Yeah.
You've heard the stories. Yeah, and so that, yeah, it was legit, right? Because they broke protocol, they had a lot of release in the plant. And so that what we were worried about was going out on the site to see if it was creeping in water or in plant vegetation or in animals, so, or in workers. So I also used to analyze a lot of urine samples and other fun stuff, so. But anyway. Yeehaw. Okay, so how are we doing? This good? So we got weaker stuff. On we go. Everybody okay with this? So I pushed you a little bit harder. Now this is all about naming because I do think sometimes I want you to be able to go backwards. Like if you heard the name, could you put the acid together? So I came up with this mnemonic and I said, if you had a grandma from the South, you get right, she's terrified of addicts. We say she has adigitis. And that's just saying if the polyatomic ion is 8, like phosphate, then you call the acid phosphoric acid. You call this a chromate, right? So this is chromic acid. If you have an ite on it, like a chlorite, then you call it chlorous acid. And then these things get a hydro stuck in front of them. That always alerts you. When I hear hydro, I know I'm just looking at something attached there. Hydrosulfuric acid. Hydrochloric acid, hydrofluoric acid. That good? That's naming. Good, 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 good. You know, and this would be good practice for you when you're like getting ready for the quiz or whatever. Just run through this slide and like pop that up and go, okay, H plus 1 is 2. 2 is less than 3, weak or strong. Strong, that's right, and it'll turn off. Oh, there it goes, popped up. Yeah. And then if you want, you can practice naming nitrate. So it's nitrous acid, right? Or nitric acid. Good. I need to practice myself. There's a nitrite. Now interesting. H plus 1? That's 2. 2 is equal to 2. Weak. And that's a nitrite. So we're going to call it nitrous acid. There you go. Good stuff. And on and on and on. And again, I always warn students, make sure H plus 1. You ready? Remember, organic chemistry has a lot of H's. How many H's are hanging out right there that I didn't even write in? 3. There's carbon with 3 hydrogens. So there's a lot of that in the structure that has nothing to do with the acid. So it's not part of the H plus 1 count, but that's okay because we don't put them first. So if it's not a H at the beginning, just ignore it when it comes to acid-base chemistry. So that's, yay, right? That makes it simple, right? Unless I drew the structure, then all you do is compare this H to these O's. But we can just get this out of the way. All the organic carboxylic acids are weak. It's just a dill. So that's easy. If it's organic acid, it's weak. All right, so let's talk about basic. This is where we kind of didn't really get into, right? Let's talk about basic. Okay. So first off, what about a base? A base will tend to precipitate a metal. When a hydroxide hits a metal, it just falls out. That was the precipitate stuff I was messing with in class, where I put two together and powder would show. If a hydroxide hits a metal, it falls out of solution. That's one thing. We use that to clean up water, so that's a common thing. In Flint, they changed the water system from acidic or basic to acidic, and that's why we couldn't keep the lead out. If you kept it a little bit basic, the lead would just have fallen out the way it had down the pipes. And so most of our pipes are coated with a little bit of hydroxide. So even in Denver, we run the water a little bit basic so that if it goes through old pipes, it doesn't start pulling metals out. So that's common. Now we know this reaction from class. This is one we want to learn, right? Acid plus base makes 2 parts. Water and just a salt, right? Just a salt. And the salt, an ionic. And you can always find the ionic by doing what? Take the metal and the H and just trade them. Right? That's what we practiced yesterday, or 2 days ago, correct? So you'll practice that a little more so you're always aware of that. But yeah, a base will always neutralize an acid, which is great. Bases also solubilize fats and oils. This we talked about in the lipid section, right? Remember the lipid triacylglyceride here? Remember this good old fat? Yeah? Remember this? The base really, and I just kind of simplified down, right? The base just inserts itself there and makes this charge such that water can grab it. So a base will actually make a fairly insoluble, because of all this hydrocarbon, it will make it soluble because it turns it from just a dipole, which is okay, to an ion, which really grabs water better. And then you can dissolve it. You guys okay with that? I say things, sometimes I look up and you guys are looking at me like, what? We did that in this class. Do you guys remember that? Is that a yes? Or does anybody need me to repeat, or does that make sense? Is that okay? Just remember, a dipole is pretty weak, like it's about 5 kilojoules. When you go to an ion, it's quite a bit of charge and water can grab it. It's like 40 to 50 kilojoules. So the whole point is this. I mean, if I'm trying to just super simplify it down, I'd go, hey, that thing, which is a dipole, gets turned into something that's got a literal ionic charge on it. And then water can grab it and it goes away down the sink. Okay. So, you don't need to know these terms per se. I'm not too worried that you know these exact names. So I'll kind of just skip over it. But here's what I do want you to understand. That's the acid. We just talked about that. It releases H plus in water. It's an acid. Good. Bases releases OH minus in water. Right? Same idea. If OH shows up in water, then therefore it's a base. And by the way, not OH, OH minus, the hydroxide on it. Is that okay? I like to get students, though, aware of this. This can get in your way. If I'm looking for something that has OH in its structure, like the hydroxide, I always look to what it's connected. It has to be connected to a metal to literally be a hydroxide. Okay. If it's connected back to a carbon, this is organic chemistry. What is this thing? What is it? Alcohol, not a hydroxide. Total different chemistry. Oven cleaner, solubilizes, right? Very hard on you. Alcohol, no big deal. We drink sometimes too much of it, but not a problem. Yes? Is that you guys understand? Not the same. How do I know that? By looking quickly. Look what it's bound back to. It's bound back to carbon. It's not a hydroxide. Bound back to metal? Hydroxide. Does that help? I do have one little weird exception, though. You can also have this guy. You have a cationic polyatomic ion. He can also bind to it. And you can have a structure like this. That also is truly a base. So watch out for that guy. So I would say bound back to carbon or ammonium. When I teach students, I always think in my head, it's like, man, how do I explain this right? Ammonium's a one-off. Being bound back to metals is millions and millions of compounds, right? That's predominantly what you see is hydroxides bound back to metal. Every once in a while, though, you might see an ammonium just like, hey, watch out for this little rascal. It also is a base. But, right, if I started saying all the different metals I could be hooked to, I could come up with quite a few. Okay. So, base or no? Yes, because it's bound back to metal. Yeah. Base or no? Now, and by the way, this is the structure. In fact, this isn't even close to a base. What is it? Carboxylic acid. It's a weak acid. That's how far away it is from being a base. It's actually a weak acid. Cool. All right. Nope. Nope. Yep. Got it? Now, there's one other category of bases that's kind of weird. They're, and I'm just going to have you do 3 of them. They don't have hydroxide in the structure, so they're mysterious that way. They're sneaky. And I'm just going to teach you 3 of them because I think these are common enough you've come across them. Ammonia, like literally ammonia, you pour on your floor. Now, hopefully the lights are coming on. It's like, oh wait, bases make fats soluble, and then I'm cooking and I get some bacon grease, i.e. fat, on the floor, and I'm like, I gotta clean this up, so I get some ammonia, and it like becomes water soluble and goes away. But if I didn't and I put water on the baking, the bacon grease, it would just sit there, right? And you'd be like, okay, this doesn't help me. You with me? So ammonia is also a base. I'll show you here in a minute how that makes hydroxide. It's not obvious, right? I don't see it in the structure. Do you? Okay, good. Bicarbonate and carbonate. Bicarbonate is baking soda. Baking soda is a weak base. By the way, they're all weak. So that'll make life easy too. Strong bases have the hydroxide in the structure. Then back to metal. Pretty much good enough. Weak bases are these 3. That's all you'll need to know. All right? All right. Let's figure out how this can make water basic. See if I got an example up here. I don't know why I repeat that, but that's okay. Okay, this is strong base, right? I see it in the structure, falls apart. You got hydroxide, that's a strong base. So if I put that in there, just like I taught you with those strong acids, that when I drop sodium hydroxide in water, I'm not thinking about having sodium hydroxide. I'm thinking about sodium floating free of hydroxide. Therefore, the water is basic, right? That's a strong base. And it's 100% falling apart. A 0.1 molar solution of sodium hydroxide would be 0.1 molar OH minus. Right? Does that make sense? If I dropped a mole of it and it all fell apart, I'd get a mole of hydroxide out of it. So whatever the concentration of sodium hydroxide, it has that same concentration of hydroxide. Is that okay? For every mole of bikes I bring into the room, I'll get a mole of bike seeds. Right? They're just 1 to 1. That help? Sodium hydroxide is the same. There's a hydroxide in every sodium hydroxide. You drop it in water, you get 1 out of it. And if it completely comes apart, boom. Yes?
Can you explain how NaOH is a strong base if the H plus rule would make the H's bigger?
H plus rule doesn't apply to this. That's for acids.
Oh, right.
Yeah.
H would be in front.
Yeah,
Right, got it.
thanks. No, I'm glad you stopped me on that, because you were probably like, you can't even think about anything else, because the
Forgot.
H plus 1 rule is not making sense right now.
Yeah.
Does that help?
Yes.
Good. Okay, cool. Get it. That's fine. Okay, here's how this weird stuff makes water basic. It creates the hydroxide out of the water itself. So see it? Here's the carbonate. Reaches over and grabs the H plus off of the water and leaves hydroxide behind. It had a 2 minus charge. Because it picked up an H plus, the charge drops to 1 minus. Easy enough? That's the mechanism for all of these. So, here we go. We're gonna try this. And there's a whole set of these in organic. It's kind of inorganic chemistry 2 stuff. I mean, they're doing that test tomorrow. And if you see students walking around, hit their head on the wall, that's my students. I'm getting them ready for a test tomorrow. I'm sorry, but you know, it's a bad time for them right now. But it'll soon be over. So if I do this, and I put it in the presence of water, and then I'm just kind of got the idea it's going to reach over and just grab that H plus off, right? And what's going to be left on the other side? How many H's does this now have on it? 4. And one of those was charged 1. Oh, that's familiar. That's the ammonium guy. He shows up. That's okay. And then the leftover is, there's the base. That mechanism's the same every time. So you need to know it for 3 things. For this, and for this. Right? So it's, you know, you can just I'm just feeling confident already. Like, okay, I think I get this. I think I can draw some products up here. Oh man. Cool. Man. Oh, you're gonna try one too? Oh, yeah, cool. Another volunteer. That's awesome. Oh, you're the best. Now, what's your question? Oh, these are, okay, hold on for a second. No, you're doing great. Explain what you mean. For acids. Oh, you're talking about an acid and a base reacting together and what you're switching. Is that what you're talking about? Oh, so I'm gonna try and follow you all. You're doing great over here, by the way. So you have an acid like this. This is an acid, right? And tell me what you're saying.
So like there's a plus sign and there's another.
Yeah. Oh, like when it falls apart?
Yeah.
Because it just falls apart in water. Yeah. So this was all together, correct? All right. So usually things just disassociate, meaning they just fall apart. So here's my acid. Well, it's not an acid yet, till it hits water and then it just falls apart. In water breaks it apart is what happens. And then this is floating around. That's literally the definition of an acid. You with me? Then there's one type of base that's very obvious. This is a different kind of base. It's still a base though, because it does the same thing. It just falls apart. And that makes water basic. I'm losing you somehow? Here, I can pretend, because this isn't really it. Sodium hydroxide would be bad for me, but I'll pretend. This would literally be what sodium hydroxide would look like if I pour it out. It would look like this. Okay? That's sodium hydroxide like this. Got it? Now when I drop it in water, which I can, by the way, this is really salt, or my hands would be burning right now. Right? You with me? And I don't know if I'm helping you. I hope I am. But when this gets in there, I put a little bit in, right? And then it just starts falling apart, and before long you see just a clear solution. Right? And that sodium is now floating all by itself, Na+, and hydroxide's floating all by itself. And that is what we call the base, OH-, because it can do stuff. Like that OH- can find a metal and make it fall down. It can get a hold of a lipid and make it charged, take a fat and make it water soluble? Is that bothering you that I'm talking about it binding back with the metal and falling down versus falling apart from the metal now, maybe? Or what part? Hey, no, I apologize. I'm not trying to embarrass you. I'm just trying to work with you and just, I get it. Sometimes, I say something that's confusing and you're just trying to sort it out.
I'll be okay.
Okay, all right. No, it's super important though. So then basically this is now the base when hydroxide's floating, right? So now if I use that same model with this, that wouldn't be obvious, right? Why does that make water basic? It's like, I don't see anything falling apart here. But in reality, these are unique because they have a different mechanism. They don't just fall apart. They literally get into the water and make the water fall apart. And when they do that, here's that same guy. Here's the hydroxide floating around. And the hydroxide has the ability to act like a base. Tear apart lipids, pull down heavy metals, et cetera, et cetera. And by the way, when I say it binds and pulls down metals, it's not any, because obviously it won't do that with sodium. It'll just stay apart from it. But it's heavy metals. The ones that are dangerous to your body are pretty simple. If you want to just a quick kind of health safety thing. See these rows here? These are very common in your body, these metals. Everything over there, not common. Now, you have some traces of copper, zinc, iron, for sure, right? But that's not because they don't float around by themselves in your body. These float around by themselves in your body doing electrolyte work, like sodium balance, potassium balance. That's how your nerves and impulses work and all that. These are bound into big proteins to do specialized things, like hemoglobin carries oxygen, right? I mean, yeah? So generally what we'd say is if this was loose in the water, it would be a problem if I just up and drank it. Even iron, which I need, if I just had a big old rusty water, just sipped it down, I'd be heading to the hospital. You with me? Okay. Hydroxides tend to grab all these and just pull them down, which is weird. These, though, they don't. They separate from it. That's why when I take sodium hydroxide, drop it in water, and then here's the base. This is kind of weird. And there's more to that, but we can't do it all in here. So how are we doing? Everybody okay on the basis? Here's the mechanism. How do we do? Oh, yeah, okay, I love this. So how many O's were on here originally? 3. So let's put 3 back on it. Okay? And how many H's did I pick up? 1. So I'm just going to do that. That's it. And you're fine. And let's think about the charge. What was it before? -2, so I picked up 1 H plus, so where does that leave me? 1 minus. And if I rearrange this a little, it'll actually look familiar to you. If you're looking at your polyatomic ion chart, that actually is that. Which, by the way, that itself also can make the water even more basic, like the same mechanism. Pick up 1 more H. How many H's should I draw now? 2. This was -1 plus 1 is 0. Same number of this. One pop spring. That's the combination.
So since it's breaking like apart the water,
Yes.
does it look like water still, like sometimes?
Yeah, if I could see that piece, it would absolutely not. But I can't see it. There's so little of that for the same reasons that, first off, this is weak. So if I'm being realistic, it looks more like this. Not very much of this occurs. Right? Just a few little bits of it happen. But I'm following your tracking there. If I could do it for the entire batch of water, yes, it would be much different. I just can't do that. Because when I drop it, it only happens on a small percentage. If I use numbers, I would say like it's 1% disassociated.
It's not taking apart all of it.
No, and that's kind of another like, whoa, right? all this weird stuff. But for you guys, that's the point I was making earlier. When we say weak base, that means I get very little of that out of there. But it does make the water slightly basic. So that is pertinent. If you have a, we sometimes purposely drink that. Milk of magnesia. Like it's barely basic. Why? Because I got to settle my acidic stomach and neutralize it without burning a hole in it. So I get a weak base and just chug it on down. Right? Or I got, oh my gosh, I got battery acid I got to get rid of, so I go get the baking soda and just pour it on there. It gets rid of all the acid, neutralizes it, but it doesn't overdo and create a basic problem. Right? It's good. You guys doing good. By the way, acid base. It's a tough concept. Trust me. It is. Like I said, that's why I'm not really joking. Chemistry 2 students, this is the toughest time for them because we're finishing acid base and then we'll work on batteries, we'll work on nuclear chemistry. They'll be like, it's easy now. Acid base is tough. Just all these weird subtleties are very confusing. But yet it's so important to us all, which is why. All right. So hopefully I didn't get too distracted. You only need to know 3 of them. Those are the 3. So ammonia, carbonate, bicarbonate are weak bases that interact through this mechanism. And if you're listening to Dallas and I's conversation, it happens to only a small percent in the water. That's why we call it a weak base. Right? And then if you just see the hydroxide in the structure, you're like, that's probably going to be a pretty strong base. If I'm being really technically correct, I would say hydroxides hooked to group 1 or 2 metals to be a little bit more precise. But I don't want to overwhelm you guys. I just want you to learn a few things. Good trends. Is that all right? So here we go. Yeah, here's one. So I'm going to drop some carbonate in there. What's it going to do, right? Mostly just be carbonate hanging out in there. But every once in a while it does this mechanism on water and I get one of these in there. But mostly I just have a bunch of carbonate floating around. No biggie. That's kind of the model. Just a small amount of dissociation. So to put it in perspective, for every 1/10 of a mole I put in, only 4 1/1000ths of it actually dissociate. Does that help see how little it has? That's a true number. I did the calculation on that one. All right, cool. That's cool, Kim, too. If you want, you can take this and figure out how to do these calculations. It's kind of cool. Small little leap. All right. Now, here I did it very precisely. The strong bases are the group 1, that's for sure. The weak bases are the ones I want you to know. And remember, they probably come into the party with some metal attached to it. They don't come in as carbonate. They come in as sodium carbonate or something, right? All right, cool. That's it. Okay, let's see. We'll practice. How are we doing on time? Oh, we're doing all right. Shall we see if we can identify? Now, I gave you only one other odd metal, right? That didn't lead with an H. Who remembers what that was? It's a way to make a weak acid that doesn't have an H in the structure. It's another weird one. I know. I gave you one more. Who's got it? You see it in your notes? That was 2 days ago. Huh? It's a group that sits right here. These guys in aluminum, when they're charged 2 and 3, they tend to make water acidic. Very weird. Has a similar kind of mechanism. It looks kind of similar, only it goes like this. I took iron 3+, and I put it in the presence of water. If I just summarized it, what would happen was it would grab a hydroxide off the water. So now I go iron plus 1 hydroxide. Now the charge, and we do this it's a weird structure, so it usually gets this kind of sign on it. It was 3-, it picks up a hydroxide, so it's not, 3+. except for hydroxide, it's now 2 plus, and then H plus is what's left floating around. Carbonates, ammonia and bicarbonate can grab H pluses off the water, leave the OH behind. These metals grab the OH minuses off the water and leave the H plus behind. Do you wonder why I'm telling you all this business like this right now? Because sometimes you guys there's metal things put in your mouth, right? And I just want to alert you that if the metals come out of this family and they get charged, they'll become acidic suddenly. And people have those kind of effects. Have you ever taken, like you said, oh my gosh, it tastes metally, right? Stuff happens, like, and you're like, it tastes metally. That's what's going on. There was acid attacking a metal and it made it a little metallic-y, and it just starts to flare up a little bit. I don't know, crazy. So that's why I thought I would show you this piece. It's a lot. Now, let's just see if we can practice this out. Let's see if we can identify. So I'm basically thinking this way. Acids, I'm looking for these things. I'm looking for the H plus or the leading H. That's easy, right? How many of those do you see up here? 2. I agree. Is everybody okay? They see 2 acids for sure. That's the easy one. Now the easy base is things that have OH in the structure, correct? But bound back to a metal and pull in the draft. How many of those do you see up here roughly? 1. I agree. Now the harder ones are this. There's also a group of metals that are that group scandium through zinc or aluminum +3, +2. And don't worry about the charge. If they're in the salt, you can assume they're the right charge. So see any of those? Anybody? Leading with what metal? Iron. There it is. Ooh, that little guy. There's a little weak acid hanging out. Then the other weird weak bases are ammonia, carbonate, and bicarbonate. Got it? How we doing? Is that organized? You want me to organize that for you on the board? Is that okay?
We're identifying if it's a weak or strong acid or base. Is that-
Correct.
Okay.
Okay, so you ready? I'll let you work these over and I'll shut up. And we'll see what we come up with. And ask if you need help. There's a flow chart for you. Take a picture of that, see if it works. You can practice with that. I just made it up. Took a trip down my brain path and said, this is, I think is what I'm doing. So you can think about that. See if it works. See if it helps. All right, how we doing? Who's got this first one? First row, either of you two, what do you got? Acid? Nope. Okay, is it a weak or strong base or neutral? Weak. It's a carbonate, right? So what is that? It's a carbonate, bicarbonate, or ammonia. What would that be? Any of you four. I'll open it up. Anybody got that? Carbonate. So it's a weak base. Okay, got that. One down. All right. Weak base. Cool. You four, you ready? What about this guy? Weak acid. Do the H+1 rule. It's equal to the O's. Perfect weak acid. I don't know if I went that direction, but oh yeah. Good. Cool. This row. Want to try this one?
Weak acid?
Weak acid, sure. Yep. Weak acid. Cool. Yes?
Strong base.
Strong base, yay. Strong base. And then last but not least, strong acid. Yay. And then the other thing I was practicing with, can you name these acids? So that'll be good practice for you too. If you know it's an acid, then you should practice naming it. Carbonate, right? So 8 becomes ic, so you carbonic acid. Yeah, okay, good. Whew, so you get some practice with this, right? And yeah, should we name the weak acid? Where's that guy at? Do we have it? Oh, this one, yeah. So carbonic acid, that's that. And then this guy, what do you do with this? Oh yeah, this was just iron chloride. Thank you. Iron 3 chloride. Thank you. That's not really, yeah, it doesn't really have an acid name. I'm just wanting to make sure you practice the acid name. Cool. All right. There we go. More practice if you want it. I'll leave that for you guys. How about it? That'll be good. I won't do it. We won't do it all right now. You guys can just check that and then practice with it. And then you get some homework and some quiz to kind of keep working on this. Ask me if you need more. If you guys feel like you need to do another couple rounds of it. Okay? Whew. That's hard work, you guys. I'm going to blow by this for a second. All right. So we're going to talk about this. This will be the next kind of a thing we're going to do. We're going to talk about pH. So you understand the pH scale. I'm also going to introduce you to something called equilibrium, which kind of is, it's a little, I'll show you. I think I can demonstrate it so you can understand a little bit. Because I do want to help you understand how you can do what we call pushing equilibrium. So we're going to work on that a little bit. But in order to do that, I'm going to do a demo. So why don't we do this? Because I feel like, why don't you take a break now? And then we'll get back and wrap our head around this demo and kind of think about that for a minute. Okay? So go take a break. You've seen me start to draw arrows. Now that you understand weak, strong base, I'm starting to say, hey, you have a reaction, and you know, as I originally teach it to students, I have them just think reactions make products, right? And that's good, that it gets you going. But then as you progress, I have to kind of show you that you can kind of make reactions shift back and forth. Like reactions can turn around and run backwards even. And if I just showed you a weak acid, I said, hey, a weak acid like HF, right? The mechanism looks like this when it falls apart in water, right? But it's wrong to think if I put a mole of this in there, it's all going to become a mole of this and this will all go away. because it's a weak acid, so really it doesn't go over much. It stays back. Understand? So we can read these this way. In fact, if I took H plus and combined it with F minus, it would make this. That would be true. That's running in reverse. You with me now? So, you guys ready? We're going to talk equilibrium. I'm going to give you words. Okay? If I think about a reaction running to products, I call it runs to the right. So if you're hanging out with chemists and they go, oh, that reaction ran hard to the right. No. You're like, what? That means it made a lot of products and there was very little reactions left over. Makes it like a strong acid. And if I say, hey, that runs hard to the left or it runs to the left, it means it doesn't dissolve very much in this case, or it doesn't react much. Okay, so those are words. I could say shifts to the right, or runs to the right, whatever. But you're going to hear that in there. I'm talking about, oh yeah, I'm trying to move it towards products. Or I could say it favors products. That's another way of saying that. And another term I could use is running backwards to the left, which means shifts left, or favors reactants. But with that, you could say this reaction runs forward, this reaction runs in reverse. And here's a good example, and I'm going to introduce that to you right now. When we talk about acid-base chemistry, sometimes you need to understand that water could fall apart, right? And that's not fair, so I'll just leave that out. Water could fall apart to an acid and a base. You know from your own experience, though, this one, you want to use your new word? It stays, anybody?
To the left.
To the left. This runs hard to the left. It runs in reverse. It favors reactants. That doesn't happen. It doesn't make much of this, does it? Thankfully, right? When I drink water, it's not like acid and base going down. I'm like, oh! I'm burning up and burning holes at the same time, right? You with me? So even though I write this reaction, it could favor staying together. So I'd say it favors being to the left. It favors reactants. It doesn't react very well. Runs in reverse. And that's true. It does run in reverse. If I take an acid and a base, I put them together, they neutralize and make water. That's what we just learned. Acid plus base makes water plus the salt. Okay, you with me? Got that term down? Now I'm going to show you that as chemists, we like to be able to know how to push equilibrium. So we learn tricks to make them go right or left. So let's make that relevant. Okay? I'm going to take something like this in my photographic solution, like old school photographic solution. It's got a lot of silver in it. That's how it makes the pictures develop. And if I put it in the presence of chloride, like table salt, it will actually make precipitate, which would pull the silver out of the water. Yay. So I'm going to put this with the right term, so that might help you. If I had that dissolved in water and I had that dissolved in water, I could make this. I would like this to run to the right. Correct? Follow my thinking? Like I want to make products because I can pull the silver out and go sell it. Yay. Right? Does that help? So sometimes you want it to run left or you want it to run right. So I'm going to show you how to kind of push equilibrium, and we're going to teach you that. So what that means to you guys is this: I might have something that's like a calcium-based material. i.e. your teeth. And they could start falling apart, dissolving. Right? And I want them to stay together, so I want to push it to the left. I don't want it to go to the right. Follow? Okay, so I'm going to teach you a little bit about that. There's a French guy that helps us with that. And I keep wandering around while I'm talking, so you know I can only see the one thing at a time. I hid my gloves in this big one because that's what I know. Correct. So this is cool. I have a couple of reactions that I think can be used to kind of teach some ideas. So I'm going to teach you how to push equilibrium. All right? So we'll start. I think the last time we were together, we were cleaning iron out of the water too. Remember that? That's cool. Let's drop down now. Remember that? I was precipitating that down, so there you go.
Is that water drinkable?
That water, I love that question. No. But yeah, it has a lot less iron than it did before. You're going to be a lot less sick than you were before. How about that?
Yeah.
Okay. And, but actually that's a beautiful example, because it pushes to the right towards the precipitate, but there's still some remaining. It doesn't go completely to the right, which is what you were asking. Now, how much it goes to the right determines whether I'm getting the clean water standards or not. So I got to get it below a certain amount. So if you looked online, you could see so many parts per million is allowed. So I got to push it at least that far. So it's a good question. If I reversed it, that stuff would go whoop, right back into the water, and the water would be colored again. That would be pushing it back to the left, running the thing in reverse. Crazy, huh? All right, well, so we'll see if we can get even crazier. We'll push your reaction. Let's see, what do I got? All right, I am going to make this stuff right here. You'll know I'm making it because the stuff I start with is yellow-brown. That's this. And I didn't put the other part in here. It's right here, it's clear. So here it is, this is clear. Is that all right? And you'll know if I make it which side I'm on, because if I'm on one side it's yellow-brown, if I'm on the other side it's going to be red. So you ready? So I'm going to make it. You certainly can't push equilibrium if the reactants aren't even in there, right? So we'll go, I think I need about 5 drops. 1, 2, 3, 4, 5. Perfect. See the difference? All right, cool. This is awesome. This is iron thiocyanate complex. It's weird because it's not all ionic and pretty. We're used to the charge balance. So this is a unique species. It didn't quite charge balance. It just stays kind of partially unbalanced, which means water can pick it up, which is nice. So it's water soluble because it has a charge on it, right? So it's pretty. And we have a lot of metals do a lot of this kind of stuff. Good, good? All right. So now what I'm going to do is I'm going to show you how to push some equilibrium. So I'll split that up. So that, and then you don't want to forget the color reference. Now I could use this, but the problem is it's thicker, so it might look darker than the other tubes. So I'll leave one of these unreacted so you know what the color reference is, right? So if I shift one way or the other, you'll see it change relative to this. Okay. So, ready for this? This is called Le Chatelier's principle. Anybody speak French in here? Just checking, because you might want to check how I pronounce that. Okay, I need help. Okay, Le Chatelier's principle says this: if you stress a system, then the system will respond by removing the stress. That sounds familiar. It sounds like us. Stress me and I'm going to figure out how to go vegetate or get away from you or whatever and remove the stress. Correct? All right. So the stress is this. Anything I do to it, it's going to move in such a way as to remove it. Okay? So that's the idea. So let's try one stress. I'm going to add more of this. So now this is already at what we call equilibrium. It's already balanced. Now, the nice thing is it doesn't mean it's all the way this way. It's somewhere favoring more this side. That's why it looks red. But there's still some of this present. So these are all present in some configuration, but I know by looking at the color, it's more to that side than this side. Everybody with me there? All right, so I'm going to stress it. I'm going to add more iron. So Le Chatelier says, if I add more iron, I'm going to move in such a way as to consume iron. Which way would that be? Left or right? I'm looking the same way you're looking, so I... Left. Right? If I add iron and it moves left, it'll suck that iron up and make more iron thiocyanate. It'll make the iron go away. Correct? Does that make sense? Okay. So if that's true, the color should go. Anybody?
Red.
More red. That's the idea. So we'll try it. We'll see if we can stress the equilibrium a little bit. Add a couple more drops. And then we'll check it against our little color reference. It's not totally obvious. Yeah, it's not bad. Can you see it? I shifted the equilibrium. Is that good? That one's, it's like, okay, that almost. So I have a magical chemical, it's phosphate, which will drop this out of solution. So now what I'm going to do is I'm going to remove the iron. I'm not adding to the iron, but I'm removing the iron. So in Le Chatelier's world, he goes, well, if you're removing the iron, it's going to move in such a way as to replace the iron. Which way would that be? To the right, which means as I remove iron, I should see the red start to go away. Correct? So I got a little of this magical powder. Put a little of that in there. See if that helps. And I don't have tons of these, but at least I can do both ways and maybe get the idea. Okay. A little bit. Just a couple crystals. See how we do. There we go. So now I'm going to start removing iron. See if we can shift. Woo! Oh! What is that? SCN. So I actually added more thiocyanate.
Oh.
I added this directly. And what did it do? Shifted hard to the right, to the left, right? I was adding the wrong chemical. I'm like, oh crap. Now, actually that works. That does what we thought it would do, correct? Shifted hard to the left. Okay. Let me get the right chemical this time. I was like, I'm having chemistry nightmares. There we go. This is a hydrogen phosphate. This is the guy I want. All right. Cool. You ready? We'll try this. Hopefully this will shift it left as opposed to farther right. And you remember what all I brought in? Cool. A little bit of this. Wait, you have it on tape. That'll be fun. I'll have to watch that later. Whoa, my. Yeah. It popped it so hard, it went on packs, right? It just completely consumed all the iron, and all that's left is thiocyanate now. Like, I mean, not all. There's some trace of iron in there. Does that make sense? I'm pushing left and right. So the general idea, okay, so now I can just walk you through, if you get the feel for this, I can either remove or add to. What if I added more of this to it? Which way would it move? So remember, I add more of this, that's the stress. Oh, this is building up, how can I remove it? If this starts building up, it goes, gosh, how can I get rid of it? Go right. If this starts building up, it goes that way. If this starts building up, I go that way. If I remove this, it goes to make more. Follow? If you need to in your notes, you can probably add it that way and just say, look, if I add more of something, right, there's equilibrium will move towards that. I mean, if I remove something, it'll move towards it. If I add it, it goes away from it to try and remove it. Okay, so here we go. We'll talk about this one for a minute. If I added more H plus, I made it more and more acidic, which way would it shift? Good. Can I see this with your hands? I saw that. That'll help. Good? Okay, good. If I add more F minus, which way would it shift? Yes. This way. Adding more will go this way to remove it, correct? The stress is, oh, it's building up. How do I get rid of it? This way, because that'll consume it, correct? If I start building up this, like adding more and more, which way would it shift? There we go. Now, what if I remove this? Which way would it shift? If I remove it, yeah, it would go this way to make more, correct? So here's a good trick. This is what every chemical engineer knows. If this is a product of value, I want to make more of it, correct? This was cost me $1, this is worth selling for $10. You with me? Then I know that as I make it, I should remove it because it'll shift to try and make more. If as I make it and I don't remove it, at some point it'll reach equilibrium and stop reacting. So that's an idea of Le Chatelier's. Okay, so that's kind of the idea. We'll work with this. Is everybody with me? The idea, get that in your notes, like, hey, whatever stress I add, it'll move in such a way to remove it. We could do tricks with that with temperature too. So this is a common thing. I'll see if I can get one of these demos. These are pretty fun to watch. You can do this too. I didn't bring one, but I feel like you guys need to see more of this. Let's kind of get used to it. Let's say that I have a reaction. It doesn't matter what it is. I'll make one up. I'll just say A plus B makes this A plus this compound. And as a result, it releases heat. You could imagine that. If I burn gasoline, it releases heat, correct? You understand that idea? So I have some reactions when they react, they create a little bit of heat. I have some reactions when they react, they create a little bit of cold. They feel cold, right? Okay. So what would happen is this. If I brought it, so remember all this is it's all in the reactor. Like all these parts are in there. That's equilibrium. So depending on whether it favors products or not, if it favors products, there's going to be a lot of this and very little of this left when it gets to equilibrium. If it's not very good, so sometimes we draw arrows like that, then we have a lot of this and very little of that made, so very little heat would be created, correct? So Le Chatelier says this. If I heated this whole reactor up, it would move in such a way as to remove heat, which would be this way. Because heat plus this makes this, so it would remove heat by going this way. But if I cooled this reaction, it would go this way, because it would create some more heat to replace it if I cooled it. Okay? So usually when I dissolve solids, this would be very common. They look like this. They're what we call endothermic. Right? So if I dissolve solids, like sodium chloride solid makes sodium plus chloride, goes into solution, and that's a pretty strong equilibrium, so it looks like this. It normally happens like this anyway. But it's endothermic. Here I'll say heat specifically. With me? So here's what I know. If I heat this up, it will move in such a way as to remove the heat by going this way. Here, this might help you. These are dissolved, right? So as I heat this up, it's going to go that way to absorb the heat. And you know this is true. If I heat something up, it dissolves better. True? Cool. There's very few salts that dissolve that have this kind of reaction. In fact, I only know of one. And that weird salt is it. I have to cool it to make it dissolve better. Very weird. Okay? You with me? That's Le Chatelier's principle. And it goes on, but I just wanted to get you used to that. Now, so, sometime in your, and I know you do this in dental school, you'll learn some of these things about teeth coming apart versus teeth coming together, right? Where you're basically having parts start to flake off, right? Losing enamel. Like ways that enamels come off versus coming on. So it's an equilibrium problem. And you want to shift it to coming on and coming together, not coming off. Okay, so that's equilibrium. All right, so we're gonna do a little bit with acid base on this. So that's kind of this. There's I have some of the math in here, but we won't mess with that. I'm going to teach you a little bit of math on acid base chemistry. And if you run through this, you'll get the pictures of what I just did, by the way. So equilibrium 1, this is actually the true concentrations, right? And then I add stress, I add SEN, so that means it's going to go like this and move to the left. True? And then when you look at that happening, here's the numbers afterwards. And sure enough, this grows and these drop. Now this is interesting. This doesn't drop because I added it, but this one will drop and this one will grow. So that's that part. But you don't have to do the math of it, but we'll move on. All right. Introduction to equilibrium. We will revisit that some more. So, here's kind of the water part of it. I will teach you a little of this math because it ends up being important. All right? No matter where we are in this with water, the amount of this times the amount of this is always equal to one number. 1 times 10 to the minus 14. It's kind of wild magic. Okay? So just bear with me. So let's just take pure water. You ready? If this is some number and these two are equal, right? In other words, when this falls apart, it equals the same number, right? So if I took this number and some number times itself equals this. Do you know how you could figure out what these are? Anybody? If this is x times x equals this, x squared equals this, how could I solve for x? Anybody know? Square root. Does anybody have your calculator handy? Let's take the square root. Because it's going to tell you the concentration of H plus and OH minus in everyday water. Ready? Got your calculator? What have we got? So you take the square root of 1 times 10 to the minus 14. Number? Perfect. Which means the OH minus is also 1 times 10 to the minus 7. Now, just to put that in perspective, because I already told you, right? You already know if it's H plus in there, that might be a problem. Let's just see what that number is. 1, 2, 3, 4, 5, 6, 7. Oh, okay. That's not very concentrated, is it? Is that all right? So pure water has a 1 times 10 to the minus 7. It's broken apart that much. That's very little percent, right? Out of 1. Is that okay? That's just a fact in water. So if I think about water, I tried to show you with a model. This isn't to scale, right? But I'm just saying, of the water you drink, it's all this except for this very, very, very small fraction that's already broken apart. Is that okay? Now, we have a scale that focuses on this part. Because that's what's really important. So really, anything that happens in your body would not be significant if that changes from there to there. Your body would be like, I don't care. I don't even know what just happened. I have no idea what happened. No big deal. But any change in your body that went from there to there could certainly be registered and you go, oh, I'm starting to get acid indigestion or whatever, right? You with me? So we have developed a scale that focuses on this, like how many zeros. And in math, when we pull down this and focus on it, it's called a log, L-O-G. So try it. Take the log of 1 times 10 to the minus 7. So do this on your calculator. And you know, you use the scientific notation, so whatever you use. What pops out? -7. Logs just pull down the power and just focus on it. That's kind of what it's doing in essence. Okay? Now, I don't know why. I wish I could visit with the scientists that did this. Okay? But they wanted to put a negative sign on that. I guess the negative sign bothered them. Okay? So, when the H plus concentration can follow, that's the acid that's in water, equals 1 times 10 to the minus 7. Instead of taking the log of that, they want you to put a negative in front. And so instead of being -7, it would now be 7. And we call that the pH scale. So when you say my water is pH 7, you can change the sign on that and say, oh, that means there's 1 times 10 to the minus 7 H plus is hiding out in there. You with me now? Now, I'm going to go a lot more concentrated, like 10 times more concentrated, and I'm going to go, okay, well, what would happen? You guys ready? Get your calculators ready. If I went to log of 1 times 10 to the minus 6. You won't have to do this long, and I bet you'll get the trend. What number comes out? 6. Okay. If I took the negative log of 1 times 10 to the minus 5, anybody want to venture what it's going to come out at? 5. Oh, so when I say something is pH 5, I'm saying the H plus concentration is 1 times 10 to the minus 5. Okay. And we worry about changes in pH from 5 to 6, because that then becomes suddenly important. So in our body, it's more like 7.4, which means slightly less than 10 to the minus 7, right? You with me? And so we don't really worry about it until we have a big jump. Okay, I'm at 7.4, now I'm at 6.4. Oh my gosh, now I need to go to the hospital. But if I was really 1 times 10 to the minus 7, and all of a sudden I changed to 2 times 10 to the minus 7, that happens all the time, every time I eat a good spicy milk. Ain't no big thing. Follow? You with me? So that's the pH scale. Yay. Okay. So, OH is hand in hand with it though. And a lot of times we don't learn this in a lot of classes. And you know, me and the other Chem 109 teacher went back and forth whether we should even bother you with this fact. But we decided we would. I know. Nice of us to take you the extra level on all this, isn't it? And we said, you know, we'll teach them how to do the OH too, because they are hand in hand. Because here's what I know. No matter what happens, if you know the H plus concentration, you take it times the OH concentration, you'll get 1 times 10 to the minus 14, always. Okay? So you actually have a way to what we call walk around the block. So I'll just show you that. I'm going to show you with a kind of a Le Chatelier's demonstration. So I'm pure water. Everybody agree this is pure water? The concentration is 1 to the minus 7. pH is 7. If I took that times some number to get 1 to the minus 14, it would be the exact same number. 1 to the minus 7 times 1 to the minus 7 is 1 to the minus 14. By the way, if you're doing 1 if you want to do this kind of math easy, it's really and if you have your calculator, you can see that. But the shortcut way to do this is you can just do whatever's down here times itself, which is 1 times 1 is 1. And then these you just add. That's how you can do that quickly without a calculator. But here we go. So you ready? Now we're going to tie it all together. At this point, the pH is 7. Agreed? All right. Now, it's at equilibrium. Now I'm going to stress it. I'm going to add acid. I'm adding some HCl. So the part that's going to go in here is this. I'm going to start adding this. Which way does it want to shift? Left. So that's going to consume this. That's going to drop. So it'll start off, and this will stay about the same, but this will drop. But together, they'll still equal 1 e to the minus 14. So I'll just prove it to you. I'll give you the real numbers and you'll see it's true. So afterwards, this is how much I added. And we already said this. All of that goes in. Point e to the, right? That shifts. That dropped. It was e to the minus 7. Now it's e to the minus 11. It's much smaller. And when I multiply them together, they still equal 1 e to the minus 14. Now I'm going to add base, not to this, but here. I'm at equilibrium. I'm going to add base. Add more of this. How's it going to shift? Same. It's going this way. You're right, because you're adding that's going to try and consume it, right? So you can imagine the same thing. Although this gets added, so there'll be plenty here, this is going to drop again. Lower than 1 e to the minus 7. These always multiply together. And by the way, let's do the pH on this one. Anybody? pH is 11. It's pH 11. I put base in there and it went up. Right? And in fact, what we learn on the pH scale, right? 0, 7, 14. This stuff is basic. This stuff is acidic. True? Now I'm going to take the weak base. Carbonate, weak base, right? It doesn't put all of that in there, right? Remember, it's not 0.01. So if I watch what happens here, it's not 0.01, it's quite a bit less, but it still shifts this way. So this is still going to drop from 1 to the minus 7, getting a little smaller. We'll see what it is. Oh yeah. But it's less than 11. It's somewhere between 11 and 10. So it's somewhere 10 point something. Right? pH. Here's a weak acid, same idea. Everybody getting the flow of this? Now, what do you want me to do with that? Okay, so, you ready? Here's the goal. We'll try and jump into this. Have a little minute. We spend a few minutes on these slides. All I want you to get out of the Le Chatelier's idea is if you stress one side of the equilibrium or the other, it'll move in such a way as to remove that stress. So get that idea, and then the other thing is I'm going to show you about pH and H plus and OH minus, and it works like this. I call it walking around the block. If you have an H plus, and please write this down because I'm going to show you a couple of formulas. We're going to learn them and work on them together. I'll give them to you on the test and stuff, but I still want you to be able to use them. If I gave you an H plus, I could get to the pH by taking true. And if I have the OH minus, I can tell you the pH, I can tell you the OH minus by going, all right, well, take 1 times 10 to the minus 14 and divide it by H plus. I'm going to end up looking at my OH minus. Now, we just need to go the other directions. And then we will almost have it all. If I knew the OH minus, and I went back this way, I would go, okay, 1 times 10 to the minus 14 divided by OH minus, brings it right back to the H plus. And if I wanted to go back this way, then what you do is H plus equals 10 raised to the power of the negative pH. With me? And there's more to the block. We call it a block because there's something called a POH. It's sitting over here, but it's just a twin to the pH. In other words, if I want to focus on how much OH minus is present, you could guess the relationship here. POH equals negative log of OH minus. That should give you the POH. Same thing. And then if I go back the other way, I could say, oh, I could find my OH minus if I just raise that to the negative POH. That'll get me here. Going this way, take the negative log. Going this way, I raise it to base 10. We'll practice. Don't worry. When we get back together, we'll practice. That's where we're diving in. This one's really easy to work across because it's plus and minus. So, 14 minus pH, POH. And if I go the other way, 14 minus POH is pH. Now you can walk around the block. Get that down. And then we're going to walk around the block, and then I think we will be done with these slide sets. It was a long slide set. And that's on here. Gives you a little practice. How we'll do that. We'll get started. This is good. Ready? I'll just start walking on some of these. Give me a concentration, any concentration of 8 plus. We got 3 minutes. We'll just walk one around the block. Anybody? Make it small. Ready? Come on, don't be shy.
1 times 10 to the negative 3.
Awesome. Ready? Cool. Ready for the pH? This is getting in my way. Negative log of 1 times 10 to the minus 3. pH equals. Anybody? 3. And if you plugged it in, like literally plug in minus log of that, and you come out with 3. Good? All right. To get from pH to POH, you just subtract it from 14. Anybody? 14 minus 3. Okay, you got that. That was easy. Now I'm going to go up to this. We're going to figure out the POH, or the OH minus. I got two different ways to do it. I'll do it this way because you probably need practice with this. I'm going to go base 10 and raise it to the negative POH, right? If you do that on your calculator, just plug it in. On your calculator, it looks like this. Just plug that into your calculator. And what do you get? 10 raised to the power of negative 11. There you go. And sure enough, this times this equals 1 times 10 to the minus 14. You'll have the formulas. We're just going to prep you. That's it. So you can start practicing. If the number was not so pretty, I'm going to just walk one through 2.5 times 10 to the minus 4. Right? 2.5 times 10 to the minus 4. Before I get an answer, I know it's going to be somewhere between 3 and 4. Based on this, I know it's between 3 and 4. Okay, somebody plug that in real quick. Negative log of 2.5 e to the minus 4. Point how much? 60? Perfect. Sure enough, somewhere between 3 and 4, right? Subtract that from 14. So if you have a calculator, it's awesome. 14 minus second answer.
10.39.
And to be exact, right, it'd be 10.4, right? And then if you walk this up that way, I'm going to raise that 2. So plug that in. And away you go. Anybody got it? 10 caret negative 10.4 equals? What was it?
4 times 10.
And it probably has more details, but that's exactly right. 4 point something, right? Get out of here. We'll get back together, and this is what we're going to end up with. All right?